is x plus 2, so therefore du is equal to dx. I seem to not be able to plug things in again. Remember that dx is the same as just writing 1 dx. Alright, last time we were able to manipulate du dx to be able to fit into that, but I don't need to do that. I can replace this here with u, but I can also manipulate this one. So I can bring this down and say, well, I can replace u with this with u. Dx is already going to be replaced with du. I have to find x somehow. And I can do this by manipulating this u. So we can say x is equal to u minus 2. And now I have everything that I can manipulate into this question changed. So, let's rewrite that. So we've got, instead of x, we've got u minus 2. And instead of x plus 2, we've got u. So let's rewrite this in. So we're going to have, let's see, u minus 2, let's put brackets around that, and where is it? U the square root du, which then we can rewrite this here as u to the power of half u minus 2 du, and now we can expand this out. U to the power of half times u gives you u to the power of 3 halves minus 2u to a half. And we're still in terms of du. So, let's start solving this, or integrating. So we integrate, we get u to the power of 5 over 2 over 5 over 2 minus 2u to the power of 3 over 2 over 3 over 2 plus c. Looks a little bit messy. So let's fix it up, simplify it up, and see if we can substitute that u back in. Remember, if we're dividing by a fraction, we find the reciprocal. So we get 2/5. Let's write this down a little bit further so I've got some space. 2/5 u to the power of 5 over 2 minus 2 times 2 is 4 over 3 u to the power of 3 over 2 plus c. So far, this integral is becoming this. Our last step here, let's replace the u function back in. Here is our u. Remember, we've got 3 different things going up here. We want the u value. So therefore, it's 2/5 brackets x plus 2 to the power of 5 over 2 minus 4/3 brackets x plus 2 3 over 2 plus c. So, there is our answer. Looks completely different to what we have here. And that's the power of substitution. It's given us the ability now to integrate something that we weren't able to do previously. Alrighty. Let's get to the second last one. Alright. So in order to do this second last one, we need to remember things such as what is the inverse of this. So we know that cot is the same as doing cos theta on sine theta. So we know that this here is what cot is equal to, because tan is sine on cos. But we've got cot 3x. So if we fix this up here, well, this here is cos 3x over sine 3x. So this integral here is the same integral as that. Now this is where we start looking at and saying, okay, which is going to be our u? Remember right at the beginning I said that if you've got something where you've got the same kind of function going on, we generally go for the denominator. So in this case, u would be sine 3x. So now I have to find what du is. So du, in this case, will be 3 cos 3x dx. So we've got our u, we've got our du. Well, I can replace this here with u, but I can't replace cos 3x with 3 cos 3x. But what I can do is I can divide by 3 again. So I'll get 1/3 du is equal to cos 3x dx. And now I have this information I can replace with 1/3 du. So let's integrate this in. We're going to have 1/3 times. Replacing that, so 1 over u, or in respect with du. So, let's integrate it. We know that we can bring this 1/3 out. And 1 over u du. We know how to integrate this. It's the same as 1 over x. So it's going to give us ln of the absolute value of u. So when we integrate this, we get 1/3 ln absolute value of u plus c. And that's given us that answer that we're looking for. Because remember, in stage 2 specialist maths, x can't equal 0, but we could make it a value that is positive by placing it into the absolute functions. So therefore, our final answer is 1/3 ln, just replace back what our u was, sine 3x plus c. And that here is doing 3 different things in one question. We are understanding that cot t is equal to cos over sine. We know that when we find u and du, we're going to have to manipulate du to fit into the equation. And because we've got something over u, we know we're dealing with a natural log. Alrighty. Cool. Let's get to the last one. So, last question. We've got a definite integral. The main difference between a definite integral and the indefinite integrals is the fact that we have to find alternative values for our upper and lower points in here. So we do the same thing as we usually do. So let's just rewrite this up here again so I'm not looking down all the time. Let's find our u and find our du. Well, u is equal to 2x plus 1 and du is equal to 2dx. I can replace u with this, but I can't replace u with 2dx because I only have a dx. What I can do is I can divide by 2 again. So therefore I get half du is equal to dx. So really, really important that we've got that kind of function here. Again, we've only got dx here, so I have to have dx by itself and I'm replacing with this. Alright, so I'm not going to go into replacing all these with u and du yet because I have a definite integral. And a definite integral tells me that I'm no longer looking at this integral in respects to x. I'm looking at it in respects to u. So that means these variables have to represent what the u value is going to be. So what we say here is